Hello from Tris, welcome back for our chemistry class. This is Organic Chemistry 1. The objective of our study, so this is our 11th lesson, and the objective of our study is to investigate the chemical properties of alkanes under what we call substitution reactions. Last time we looked at combustion of alkanes, and we said that combustion of alkanes can occur under complete combustion or incomplete combustion. Now, today we want to look at what is called substitution reactions. So, just the way the name suggests, substitution reaction is one in which a hydrogen atom of an alkane is replaced by a halogen in the presence of ultraviolet light. So when we talk of substitution, it is where one of the hydrogens in the alkanes is replaced by a halogen atom. And this reaction occurs in the presence of sunlight. So we are talking of halogen, a halogen atom replacing a hydrogen atom. That's one. And the condition for this reaction, the condition for substitution reaction, is the presence of UV light, what we call the ultraviolet light, or you can simply use sunlight. So this reaction requires sunlight. The reason why sunlight is required is because alkanes are less reactive. They are somehow inert. So alkanes react with halogens only in the presence of ultraviolet light to form halogen alkanes. That is another point. Now, what happens during the substitution process? How does the substitution occurs? That is what I want to explain step by step, how the substitution takes place. Now, the substitution occurs, one, sunlight is required or ultraviolet light is required. But what is the work of this ultraviolet light? We know that halogens exist as diatomic molecules. Halogens exist as diatomic molecules. If it is chlorine, it is Cl2. Fluorine, bromine, like that. Meaning here, we have chlorine covalent bond. In fluorine, we have fluorine covalent bond. And the same applies to, so normally, the sunlight is required to split the molecules, the halogen molecules, into free radicals or free atoms. So the role of sunlight is to split the halogen molecules into free radicals. So these are called free atoms or radicals. Now, these free radicals are highly reactive. And because they are highly reactive, they can therefore move and attack So first, the splitting of the halogen molecules. That is first step. Second step, the free radicals or the free halogen atoms knock and or remove one hydrogen from the alkane, leaving an alkyl radical. Leaving an alkyl radical. I want to use an example here. First, we have chlorine being split into that way. So these are free radicals. Free radicals. Then the free radicals, if for example we have methane, let's say this is methane, the free radicals will move and then they will start to form a bond with the alkane. As a bond is formed between the free radical, chlorine radical, and the carbon atom of the alkane, one of the bonds between the hydrogen and the carbon will start to break. So one of the bonds between carbon and hydrogen breaks, while a new bond is formed between the chlorine radical and the carbon atom. So this one will continue to break completely, and this hydrogen will become free, while this bond will form completely. So at long last, this hydrogen will remain free, but this chlorine, having formed a complete bond, will get attached there. So what will remain with is alkyl radical, because once this hydrogen goes away and you have a chloride there, this one is an alkyl radical. Go and reflect back, read back on your notes on the alkyl groups. This one is CH3 group, methyl. So that is what happens. Now, the last part, Roman 3, that is step 3 from our screen. The alkyl halide, so the alkyl radical combined with the other free halogen atom or radical to form halogenoalkane. So again, this alkyl radical will combine with the chlorine to form an haloalkane, that is halogenoalkane. So that is how the reaction occurs. So the chlorine atoms substitute repeatedly in the alkane. Each substitution removes a hydrogen atom from the alkane and form hydrogen halide. So if we have excess, in case we have excess chlorine, this one will be substituted, this hydrogen will be substituted, and this one will also be substituted. Meaning you'll have chlorine here, chlorine there, and chlorine there, as long as there are excess chlorine molecules to continue with the substitution process. So the substitution is continuous. It is continuous until all the hydrogen atoms are completely substituted. Now, I want us to look at, so the substitution stops when all the hydrogen, in the alkanes are replaced with halogens. So So substitution reaction is highly explosive. Normally it occurs very fast in the presence of sunlight or UV light. So the catalyst here is UV light. That is one condition which must be present. This reaction cannot occur in the dark. In the dark, no substitution reaction of alkanes. But in the presence of sunlight, it will take place explosively. Our first example is going to be the reaction of methane with chlorine and bromine. So in our first example, we are going to look at the reaction of methane and chlorine. Can we talk of excess chlorine? Excess chlorine. Now in this case, this reaction occurs in steps. So it takes place in steps. So in step one, we'll have methane reacting with chlorine to form. Now one chlorine will come here and substitute one hydrogen. So instead of having 4 hydrogen, we'll have 3 hydrogens. Then chlorine will take its place. Now, the hydrogen from here will combine with the one chlorine to form hydrogen halide. That is hydrogen chloride. So this one is a gas, a gas, a gas, a gas. Now, then the next thing we are going to write is in terms of open structure. So we are going to do this in our next video, but drawing the open structure. So let us again connect in the second video.